Now, this short video is concerned with designing for fatigue under fluctuating wind loading from atmospheric turbulence. And it looks at a simplified approach to the problem, which is actually pretty complicated, that could be very useful for design purposes. Now, this is a kind of stress variation that we might usually associate with fatigue, a sinusoidal variation with time. And of course, this is the kind of stress that fatigue strength tests impose specimens to. However, stress history under wind loading looks a bit different. It's essentially a random process. We have a mixture of different frequencies, high and low frequencies, within the wind load or wind stress variation. But buried in those histories, you will see some effective cycles, stress cycles. So we can see a ring there. What we have to do is to try to make use of standard fatigue strength curves, which are based on sinusoidal stress variation, trying to make that usable in a wind loading context. These pictures show some examples of where fatigue cracking has actually occurred. In fact, the one on the left, we've had a failure also. Now, typically these are slender structures like light poles or possibly electricity transmission poles. And they've got a feature in common that there's local stress concentrations, which is where the cracking will occur. Now, resonant dynamic response to wind will play a role, but it's not actually the only mechanism that's producing it. We can actually get random cycles produced just by the turbulence, what we call background or sub-resonant fluctuations. Now, this is a very useful plot on this slide here. It shows a number of cycles to be expected for a given stress range, where the stress range is being plotted as a percentage of the maximum stress in a structural lifetime. In other words, the one cycle stress on the ordinate of the graph there. So you'll see that we expect to get 50% of the maximum stress producing 1,000 cycles. They're ringed on the graph there. Now, this graph and function originated in Europe in the 1980s in a publication by the European Convention for Structural Steel, and then later on it appeared in the Eurocode for wind actions and the Australian-New Zealand standard for wind actions. They're listed down the bottom there, and you'll also see the equation for the curve shown at the bottom of the slide. Now, in the next 3 slides, we'll look at the sensitivity of the fatigue cycle count graph that we showed in the previous slide to wind climate and the dynamic response parameters of the structure. And these slides or these comparisons are taken from a paper which is shown on there that was presented in 2012. You can download that paper from a couple of websites down at the bottom there. Now, on the left-hand side, you can see the expression for the Weibull probability distribution. So the equation gives the probability of a wind speed, and here we're talking about typically a 10-minute mean wind speed exceeding a certain value over time. And in the right-hand side there, we have the exponential expression where K is the shape factor and C is the scale factor. So it's a 2-parameter Weibull distribution. Now, this graph shows the calculated stress ratio versus number of cycles graph for 3 different values of the shape factor K. A bit hard to read there on the slide probably, but K of 1.5 is the green line, K of 2 is the red line, and the blue line is shape factor of 2.5. And the black dashed line is the universal line that was shown a couple of slides ago, which is pretty much on the conservative side, as it gives you a bit higher number of cycles than we calculated, certainly for the 1.5 shape factor. But generally it's a pretty good match. Now the bottom right graph there, we have a similar comparison for this universal dashed line compared with the calculated cycle count for 3 different values of scale factor, 4, 6 and 8 meters per second, which are typical values for a height of 10 meters over open country terrain. And again, there's a pretty good comparison there. The dash line is slightly on the conservative side of the low stress range, but otherwise it's quite a good match. Now this expression shows our assumed relationship between stress, wind-induced stress, and the mean wind speed. So it's a power expression with an exponent n. Now when n is equal to 2, that would imply that we have no resonant response. Essentially it's just the, if you like, the quasi-static relationship between wind loads and stress and wind speed. Now if n is greater than 2, that means that there's some resonant response going on there. Typically it's probably not going to exceed 2.5. 2.5 would indicate a high amount of resonant response. So this graph now that's on the right hand side shows the calculated fatigue cycle count for 3 different values of the exponent n, 2.0, 2.2 and 2.5. Now this is for a particular couple of values of shape factor, Weibull shape factor and Weibull scale factor. Shape factor of 2.0 and scale factor of 6 meters per second, but these are typical values. Now the calculated fatigue cycle count curves are quite well represented by this universal black dash line there. Not much sensitivity at all to that exponent. So this plot shows the sensitivity of the cycle count to the life of the structure, big T. The 3 values, 25, 50 and 100 years. And as you can see, there's very little sensitivity to that structural life, bearing in mind that the stress ratio on the ordinate is the ratio of the stress range to the maximum stress in the time t. And again, the universal dash line actually fits quite well, slightly on the conservative side. Now moving to the fatigue strength side, this graph shows a set of SN lines, or stress range versus number of cycles for failure. And these are typical of information you'll find in various codes and standards. These happen to come from Australian Standard 4100 and Eurocode 1993. Now these, the stress range and the number of stress cycles are plotted on log axes, as you can see. And each line represents a particular detail category, which is the stress range for failure at 2 by 10 to the 6th cycles. And each line has 3 segments. There's the first segment with a slope of -3 goes from 10 to the 5th to 5 by 10 to the 6th cycles. Then there's a slope of -5 from 5 by 10 to the 6th to 10 to the 8th. And then beyond 10 to the 8th, the slope is 0. So what we have now in summary are, on the left, a universal stress cycle count due to wind, which is the stress range normalized to the maximum stress in a lifetime against the number of expected cycles. And then on the right we have a family of similar fatigue damage curves, or SN curves. Now that combination of a single universal stress cycle count and a family of parallel SN lines actually leads to a very simple and straightforward design method, which we'll discuss in in the next couple of slides. So the next step is to compute accumulated fatigue damage using minus rule. So the loading comes from the stress cycle curve that's in the wind standards, and the damage, or the number of cycles for damage, of course, comes from the SN line. So if you do that, you end up with the graph shown on the left. Damage against the ratio between the maximum stress in the lifetime T and the detail category, which defines the particular SN line. And because we have a single stress cycle, non-dimensional stress cycle line, and we have a family of similar SN lines, we end up with a single damage, or a universal damage rate curve, as shown. Now on the damage rate curve, a value of damage of 1.0 indicates failure due to fatigue. And with the assumption of the cycle count line, the universal cycle count line, and the family of SN lines that we showed earlier, for that combination, failure will occur at a ratio of maximum stress to detail category of 3.65. If you have a different family of SN curves, there will be a different failure point. So now we come to the final stage, which is to relate the universal damage curve, which will predict failure at a particular stress ratio, or stress range ratio, to the static design for that particular detail. And the mathematics that's shown there actually comes from the paper on the left, which is published in the Journal of the Australian Steel Institute, Steel Construction, from August 2012. So what you see at the top there is the equation F subscript WF is 5 times the detail category. FWF is the unfactored ultimate design stress. We've called it ultimate wind equivalent fatigue stress capacity, which is a bit long-winded, but if you look down the bottom, you'll see the relationship between FWF and FW star, which is the stress produced by the ultimate design wind load. And the phi factor can vary depending on whether the member is redundant or not redundant, you see from the bottom. So you may ask the question, why isn't that 3.65 at the top instead of 5? Well, the reason is that the FWF is related to the maximum stress, not in the maximum stress in the lifetime, but the maximum ultimate stress, which is the expected maximum in a much higher period. For example, in Australia and New Zealand, we'd use 500-year recurrence interval wind speeds. So it's essentially the maximum stress in a period that's roughly 10 times the life T. And that relationship is down the bottom there. And for most locations in Australia and New Zealand, that's around about the ratio, 5 over 3.65. So it's been simplified, and this explains why we have a 5 in the top equation instead of a 3.65. Well, what I've given you here is a short summary of a design method for predicting fatigue, damage and failures under turbulent wind loading. Now these typically occur at critical points in the structure where you have a stress concentration. We have plenty of examples of where these failures have occurred in typically slender structures. Now the method is based on a single so-called universal stress range cycle count under wind loading, which is originated in the 1980s but is now in the Eurocode for wind actions and the Australian-New Zealand standard for wind actions. Together with that and a family of 3 segment fatigue lines with different lines representing different detail categories, we can come up with a very simple relationship between failure stress and the detail category. We showed that earlier, and then the last step was to relate that to the ultimate or static design stress. So I think this is quite a useful design tool that avoids having to do a lot of numerical calculations. We've already done the numerical calculations to get that damage rate curve that I showed earlier, so it's already been done. You don't need to repeat it, and so it makes prediction of fatigue, damage and failures quite simple, relatively simple. So the universal cycle count for wind loading, together with that particular set of 3-segment fatigue strength lines from AS 4100, gives you a failure at a stress ratio, the maximum stress over the detail category, of 3.65. I showed that earlier. And that can be then extended to related to the static stress, ultimate stress. And that factor turns out to be 5 instead of 3.65, as I showed earlier. So we have this quite simple rule that makes fatigue design quite workable. The last comment I make is that we've dealt with fatigue under turbulent wind loading, which is typically a long wind, but it could be crosswind if it's produced by lateral turbulence. But we're not talking about vortex-induced vibrations, which will produce crosswind responses of certain slender structures. That occurs over a narrow range of wind speeds, which has not really been treated in this presentation here in this method.